welcome back once again to Ask IITians. In the previous lecture, I told you something about the law of equipartition of energy. To continue the same thing in this lecture, now I'll be telling you something about what do we mean by DOF, to complete the form as degrees of freedom. I'll try to introduce you what do we mean by degrees of freedom and how are we going to calculate the degrees of freedom for various different kinds of molecules. For example, I'll be taking into account the monoatomic molecules, diatomic and then polyatomic molecules. So let us begin up with the today's session so that we can discuss certain questions regarding to this topic. So students, now let us begin with another topic where we are going to discuss something about the degree of freedom. Now let's start with the topic. First of all, let me define what do we mean by the degrees of freedom. So I'll simply say that the degree of freedom is basically defined as a number of the independent ways in which an atom or a molecule can absorb or release or store the energy. Let me for example say that suppose there is a point in the space. Then to represent that particular point in the space, you need to know the three coordinates. That means you should know x, y and z coordinates in order to completely define what is the address of that particular molecule or that particular point in the space. So in the way of telling something about the address of the molecule, you need to know certain number of coordinates. And that certain number of coordinates can be simply taken in analogous to something which is known as degrees of freedom. So, the degree of freedom of any particular molecule is basically defined as the number of independent ways in which an atom or a molecule, whether that atom or the molecule can absorb or can release or can store the energies. So, all those number of independent ways in which an atom, molecule or a molecule can absorb, either it can release or it can store the energy is what is known as degrees of freedom. Now, monoatomic gas, if I take the example of any particular monoatomic gas, helium, neon or argon, I will simply say that the number of degree of freedom is 3, that is 3 directions of translational motion can contribute to the translational kinetic energy as which is represented in the figure. Now see, for example, any particular monoatomic gas can be simply taken to be an atom. And if you know an atom, you know that an atom can either translate in x-axis or it can translate in y-axis or it can translate in z-axis. That means it will have velocity either in x-axis written as vx or in y-axis vy or in z-axis vz. That means if I am simply taking the case of any particular monoatomic gas, there will be 3 different degrees of freedom that will be necessary. And why so 3 degrees of freedom? Because there will be 3 directions of translational motion which is going to contribute to the total kinetic translational energy of the molecule. Now once we are done with this case of monoatomic gas, now let us come over to the case of a diatomic gas. For example, if you have a diatomic gas like hydrogen, that means there are 2 atoms. Now this molecule as a whole can either move in x-axis or it can move in y-axis or it can move in z-axis. That means again this particular molecule is going to have 3 translational degrees of freedom. Now if I say the number of degrees of freedom, so first of all let me talk about the translational kinetic energy. So there are going to be 3 translational kinetic energy terms and hence the number of degrees of freedom in the case of translational value will be 3. Moreover, the rotational kinetic energy will be 2. Why so? I am asking the molecule has a total number of rotational kinetic energy terms is 2 because there will be 2 ways in which a molecule like this, a diatomic molecule can rotate. Either it can rotate about this axis or it can rotate about this axis. Since there are 2 different ways in which a particular molecule can show its rotation, so the rotational degrees of freedom in the case of a linear diatomic molecule is 2. So if I'll say the total number of degrees of freedom will be 3 plus 2, that is going to be 5. Let us look into the diagram once again. For example, this hydrogen molecule either as such as a whole, it can go in the x-axis or it can move in the y-axis or it can move in the z-axis. Moreover, as per I told you, either the rotation can be along this axis or the rotation can be along this axis. So since there are 2 different axes about which rotation can take place and hence rotational degrees of freedom will be 2 in number. Now moving ahead, Let us come over to something which we mean by polyatomic gas. Now polyatomic gas, either it can be a kind of linear molecule or it can be a kind of non-linear molecule. For example, water is coming under the example of non-linear triatomic molecule, whereas carbon dioxide is coming under the example of linear triatomic molecule. Again, ammonia is coming under the example of non-linear, but this is not a triatomic, so we simply call it as a polyatomic molecule. Now, how are we going to define the number of degrees of freedom? Again, any particular molecule, whether it is linear, whether it is non-linear, whether it is monoatomic, diatomic or polyatomic, it can have only 3 translational degrees of freedom, because as a whole, the molecule can either move in x-axis or it can move in y-axis or it can move in z-axis. So, if I am taking the case of water, water as a whole can either move in x-axis or it can move in y-axis or it can move in z-axis. So the total translational kinetic energy terms will be 3. Now if I am asked to find out what are the total rotational kinetic energy terms, I will simply say that taking the case of water, either it can rotate along this particular axis or it can rotate along this particular axis, or there will be a third axis passing through this oxygen. That means there will be 3 different axes along which the rotation is possible, and hence there will be 3 rotational degrees of freedom. So overall there will be 6 total degrees of freedom. And the same has been represented here in the figure also, that you have this water molecule, either it can move in Vx with Vy or Vz, that means corresponding to 3 translational motions. Similarly, either the rotation can be along x-axis, along y-axis or along z-axis, and hence 3 rotational degrees of freedom. So overall of 6 degrees of freedom in totality. Now having done with this, now there is a table which has been given here, and the degrees of freedom for various different molecules have been given out here. Let us take into account all these degrees of freedom one by one. First of all, let us come over to the category molecule, where we have different kind of molecules. We can have monoatomic, diatomic or polyatomic molecules. Now the examples for monoatomic is helium, for diatomic is hydrogen, and for polyatomic it is water. Now if I ask you to find out what are the degrees of freedom, we have now discussed about 2 kinds of degrees of freedom. One are your translational degrees of freedom and another are your rotational. So if you combine the 2, what you get is the total number of degrees of freedom. For a monoatomic gas or a diatomic or a polyatomic, this is as per what I told you, the total number of translational degrees of freedom is going to be 3 only. Because a molecule as a whole can either translate in x-axis, y-axis or z-axis. So if I am talking about the rotational degrees of freedom, since you know that rotation is always defined with respect to another molecule. So if I am just talking about a monoatomic molecule, that means there is just one particular atom in the molecule. There is no other atom corresponding to that atom. So there won't be any particular rotation of that atom, because for rotation you need an axis with respect to another molecule atom. Now if there is no other atom, so the rotational degrees of freedom for a monoatomic molecule is 0. For a diatomic molecule, since I told you there will be 2 axes, 2 perpendicular axes about which the rotation is possible, so the total number of degrees of freedom are 2. And the polyatomic molecule will have 3 total number of rotational degrees of freedom. Now if I ask you to do the totality, 3 plus 0 is going to give you 3, 3 plus 2 is going to give you 5 and 3 plus 3 is going to give you 6. Now, as per the law of equipartition of energy which we have discussed in the previous slides, I can very easily write the total kinetic energy per molecule is nothing but 1 by 2 of kBT times the total number of degrees of freedom. That means now total number of degrees of freedom are 3. So the total energy is 3 by 2 kBT, and this comes from the fact 3 into 1 by 2 kBT. Similarly here the number of degrees of freedom are 5. So the total kinetic energy is 5 into 1 by 2 kBT, which is nothing but 5 by 2 kBT. And for polyatomic molecule you have 6 into 1 by 2 kBT, which comes out to be 3 kBT. Now, all these values have been taken at a temperature of 300 Kelvin. So, once we are done with this, let us try to discuss little more details of these topics. So, degree of freedom depends upon the absolute temperature of the gas, because this is what I told you. Degrees of freedom is the number of independent ways of representing any particular molecule. So, as per the fact, it is based upon the absolute temperature of the gaseous molecules. Now, let us take the example of a diatomic gas, hydrogen. If you are taking the example of the diatomic gas hydrogen, hydrogen gas have the vibrational kinetic energy also, as which is shown in the figure. See, that means if you are having a hydrogen molecule, and with respect to calling hydrogen molecule as such, I mean that there are two hydrogen atoms which are joined together by some force of attraction. That force of attraction never means that there is a kind of a string that can be just taken as analogous to that there is a kind of string which is attached between these two atoms. So, if there is a kind of string which is attached between the two atoms, one atom as well as the other atom both are vibrating with respect to one another. So, if both of them are said to be vibrating with respect to one another, they will said to have vibrational kinetic energy associated with them. So, where this contribute 2 degrees of freedom which correspond to the kinetic energy and the potential energy associated with the vibrations along the bonds between the two atoms. So, now looking into the picture, this is very much clear to you that if I am talking only at the temperature nearly 250 Kelvin, the degrees of freedom is going to be 3. At 250 to 750 Kelvin, the total number of degrees of freedom is 5. Whereas if I am talking about more than 750 Kelvin, the number of degrees of freedom is 7. This proves the fact that any particular degree of freedom, the number of degree of freedom for any particular molecule is completely dependent upon the temperature. And why is this so? This is because the energy of the molecule is distributed as the translational kinetic energy. You can also have rotational energy, you can have vibrational energy. Now, depending upon the temperature of the system, the number of rotational and vibrational degrees of freedom, they do change. And once you will get the change in the number of rotational and vibrational degrees of freedom, that means the overall number of total degrees of freedom will also be changed. And hence, this is the basis of this particular observation. Now, another thing we have is, again we have monoatomic, diatomic and polyatomic molecules, and this is the degrees of freedom which I am talking about. So, the average, since we know that the monoatomic has 3 degrees of freedom, so the average kinetic energy is 3 by 2 kBT, and hence the total internal energy is nothing but the internal energy of Avogadro's number of molecules. So, it is 3 by 2 R2. For a diatomic species, the total number of degrees of freedom is 5. If total number of degrees of freedom is 5, the average kinetic energy per molecule is nothing but 5 into 1 by 2 kBT. So, it comes out to be 5 by 2 kBT. And if I am talking about 1 mole of the gaseous molecules, the answer will be 5 by 2 RT. For polyatomic, the number of degrees of freedom is 6. Average kinetic energy per molecule is going to be 6 into 1 by 2 kBT, which comes out to be nothing but 3 kBT. And hence, for all the molecules or for Avogadro number of molecules, you have 3 RT. So students, you need to keep in mind this table also, as well as the different cases, whatever we did for monoatomic, diatomic as well as polyatomic molecules. Now let us consider one particular example so that whatever we have learned, let's try to clarify all our concepts with this help of question. So the example that has been stated here is a vessel contains an ideal. So now it is clear that you have an ideal gas and that too a diatomic gas. So you have an ideal diatomic gas which is contained in the vessel and the temperature is given to be 220 degrees Celsius. So which can be written as 273 plus 20, that is 293 Kelvin. The total translational kinetic energy of the gaseous molecule is given to me. So we have been given the value of total translational kinetic energy. The mass of the gaseous molecules is then doubled and the total translational kinetic energy of molecules has also been given a value of 9 into 10 raised to the power minus 6 joules. You have to determine what is the new temperature of the gas. So students, this question is simple enough, but the way to do this question is you need to simply first pen down all the points, all the data values which are given to you, arrange the values and hence find out the value of unknown. So let me first of all pen it down. The first temperature is given to be 293.15 Kelvin and the energy E1 is given to be 3 into 10 raised to the power minus 6 joules. Finally, E2 is given to be 9 into 10 raised to the power minus 6 joules. Now, if I simply ask you to apply the formula for the total translational kinetic energy, I will say E is nothing but 3 by 2 into N into kBT. Now, once you know this thing, you know the value of N is given as given mass divided by molar mass into Na. So now, if I ask you to write this down or further continue with this, you know K is also written as R by Na. So solving this value further, you can get E is equal to 3 by 2 into M by capital M into Na. So I am just substituting the values which have been given to me as the data points in the question into R by Na multiplied by T. So the value reduces to be 3 by 2 into M divided by M into RT. Now if I simply ask you to substitute the values of data points that has been given to you, I will say at temperature T1, the energy E1 will be 3 by 2 into, let's say the mass, given mass is M1. So M1 by capital M into R into T1. Now if I ask you to find out the value at temperature T2, which is what we have to find out. So E2 will be written as 3 by 2. Now since it is said in the question that the mass has been doubled, so we can say 2 times of M1 divided by capital M into R of T2. If I ask you to take the ratio, you get E2 over E1 as 2 times T2 over T1. So 9 into 10 raised to the power minus 6 joules divided by 3 into 10 raised to the power minus 6 joules is 2 times T2 divided by 293 Kelvin, or you can also take 293.15 Kelvin. On solving this value of T2, this joule got cancelled, so you'll get 9 by 3 into 293 divided by 2. So on solving this, you get the value nearly 440 Kelvin, or which corresponds to 167 degrees Celsius. So students, this was all about the degree of freedom for any particular gas. Now solving this question made us more powerful and made us more confident that we'll be able to do all such questions of this type. So students, as per you have seen, we have discussed something related to what do we mean by degrees of freedom. We have also tried to attempt certain questions regarding the same topic. Now, since we are done with this particular thing, it's a time that in the next class we should move on over to some of the questions which have been asked in previous year exams. So by the time, you please stay tuned, revise whatever has been taught to you, be prepared for certain questions in the next class. So stay happy, and I'll be meeting you in the next session.